section 4.2 is about logarithmic functions. Remember from the previous section 4.1, I was talking about the exponential functions. So an exponential function was a function of the form f of x equals b, a number b raised to the x power. Now, what did I say was a special, what the logarithmic function basically was? It is the inverse of the exponential function. Now, how do we get the inverse of a function? So we're going to go through the procedure again. So which is y equals b to the x power. To get the inverse of the function, what we need to do is we need to interchange the x and the y values. So that's going to give us x is equal to b raised to the y power. Okay, so and then we needed to solve for y, but in reality the logarithmic function can be expressed in two different ways. One of the ways that the logarithmic function can be expressed as is in what we call the exponential form. So this one that you see right here, it is already my logarithmic function because we obtained it by switching the x and the y, by interchanging the x and the y, which is basically how we get the inverse of a function. Okay. Now, this is called the exponential form of a logarithmic function. Okay. Now, the logarithmic function can be expressed in another way. It can also be expressed in terms of y equals. Okay. So just remember right here, based on what we see on this function, what does the y represent in this function? The y represents the power. So when I say y equals, I mean that the power. So whatever the logarithmic function is going to represent the power of the function. That's basically what the logarithmic function is for. So we're going to abbreviate the logarithmic function with the log. Now we have a base. You see that the base is my b right here. So the base, we're going to write it as a sub-index. This is the base that you see up here. This y is the power of the logarithm. So anytime I see the logarithm represents a power. Okay? And the number there's a number right next to the logarithm, which is going to be my x. That's going to represent the result of raising this base to that answer for the logarithm, which is the power. It gives me this result, which is x. This is called the logarithmic form. So the first thing we're going to be looking into is how we can interchange from the exponential form to the logarithmic form and vice versa. So let me give you the formal definition of the logarithm. It tells you that for x greater than 0 and b greater than 0 but not equal to 1, we already talked about the base before. We said that the base was a number greater than 0 but not 1. We're not interested with a base of 1. Then the y equals log base b of x is equivalent to b to the y equals x. This is called the exponential form. This is called the logarithmic form. So the function f of x equals log base b of x is the logarithmic function with base b. So the first things that we're going to do in this section is that we're going to interchange from one form into the other form. First question is that we need to rewrite this expression in its equivalent exponential form. So keep in mind that this is the base right here. The number on the other side of the log, this is your power. And the number right next to the log, this is the result. That's what I told you when we were talking about the logarithm. So if I want to write this in exponential form, it would be the base, which is 2, raised to the power of y, gives you a result of 8. That's basically what the exponential form is going to be. Now, we could be able to solve this, but the question is not solve this equation. It just says write the following equation in exponential form. So we just need to write it in its equivalent form in exponential version. Now, we're going to do the opposite on the next problem. Now, what we want to do is we want to rewrite this equation in its equivalent logarithmic form. Now, To write it in logarithmic form, we're going to do the exact same thing. Now we know that this is the base right here, and this is the power, and this is the result. So when we write any expression in logarithmic form, the number on the other side of the equal sign, it is going to be the power. Then we have the L of G. The sub-index on the bottom is going to be the base. And the number right next to the logarithm is going to be the result. So this in logarithmic form is going to be the power, which is 7, equals to the log base of y. The base is the y of the result of 770. So we read this the following way. When I raise the y to some power, it equals to this result of 770, and that power is 7. That's what it tells me right here on the original equation. Okay, so I'm just gonna write it without all those words. So 7 equals log base y of 770. This is the equation in its equivalent logarithmic form. Now, the next thing that we're going to do is now we're going to be evaluating logarithmic expressions without using a calculator. Now, this one says log base 2 of 1/4. We want to evaluate this expression. Now, what do we know about this 2? This 2 represents the base, and this 1/4 represents the result. So anytime we are evaluating a logarithmic expression, we're always finding the power. So if I want to evaluate this logarithmic expression, what we need to do is I need to find a power that when I raise this 2 to that power, it gives me an answer of 1/4. Okay, so we know by definition that 2 raised to the second power equals 4. But now this is a 1/4. What causes a number to become the reciprocal? We talked about this rule before. Anytime I have a number raised to a negative exponent, that represents the reciprocal of the number. So basically, that means that this power, 2 raised to the negative 2 power, equals to 1/4. The negative makes it become the reciprocal of 2, which is 1/2 squared, which is 1/4. So the answer for this logarithmic expression, it is always going to be a power, and that power that makes that 2 to be equal to 1/4 is 2 to the negative 2 power. Okay. Now, we're going to do the exact same thing here. On this one, we're going to apply another property that we learned from exponents back in section P.3. On this one, we're trying to find a power that when I raise the 2 raised to that power, it gives me an answer of the square root of 2. And we talked about this definition a long time ago in section P.3. A number raised to what power is going to equal to the square root of that number? We talked about it in section P3. Any number raised to the power of 1/2 is going to equal to the square root of the number. So in this case, that power, 2 raised to what power equals the square root of 2? 2 raised to the 1/2 power. So that means that this log, the value of this log is going to be not negative. It's going to be positive 1/2. And that concludes this question. Now, the next one. We're going to evaluate this one. It says, evaluate the following expression without using a calculator. This one is kind of very similar to the previous question. It's actually the same thing, because if you notice, on this one we're trying to find a power that when I raise the 81 to that power, it equals to 9. Okay, so that power is also going to be a 1/2, because what does the 1/2 mean? The square root of 81. That 1/2 means the square root of 81, and that is going to give us that 9. Right? So the power for this expression is going to be also a 1/2. Next expression. Before going into this, we're going to go ahead and look at some special properties. This one says evaluate the expression without using a calculator. So before I show you the special properties, we're going to take a look to this the way I was doing it so far. This expression means that I'm looking for a power that when I raise the 8 to that power, it gives me a value, an answer of 1. And remember that what power is always going to give you an answer of 1? 0 power. Now, not only for a base of 8, if I have a base of 9, if I have a base of 10, any number raised to the 0 power, it equals to 1. So this is going to be a special property that tells you that if I have the log, no matter what the base is, but the result of that is 1, the power that makes any base to be equal to 1 is going to be a power of 0 for any base. That is one of the special properties that we're going to cover in this section. Next special property. Now we have log base 7 of 7. Now, what does this expression mean? It means that we're looking for a power that when I raise the 7 to that power, it gives me an answer of 7. And that power is going to be a 1. And not only for base of 7, but if I have any base, okay, so if I have this expression in this format, the log of any base of the same number, you know, the power that is when I raise the power that when I raise a number to that power and it equals to the same number is always going to be the first power, no matter what the base is. But if the base and the result are exactly the same, the power that makes them to be equal is going to be power of 1. Okay? This is the second special property. Last but not least, we got one more special property. This one right here has a special name. This one is going to be called a common logarithm. A common logarithm, it is a logarithm that utilizes a base of 10. Now, you see that this logarithm does not give us a base right here on the bottom. So that means automatically that it is called a common logarithm. If there is no base, by default, it is going to be a base of 10 down here. So that's what makes it a common logarithm, because it is the base that we use commonly in our number system, bases of 10. The digits, the tens, the hundreds, the thousands, and so on. 10 to the 0 power, 10 to the first, 10 to the second, 10 to the third, and so on. So it is called a common logarithm. Okay. So on this one, it is another special property, because if you think about it, what does this one mean? That we're looking for a power of 10, that when I raise the 10 to that power, it equals to 10 to the 6th power. And that power is going to be, and that will be, of course, a 6. Because 10 to the 6th power is going to equal to 10 to the 6th power. Right? So what does this tell us? This is also a special property. It tells us that anytime I have a log of some base, of that same base raised to a power, the answer would just be that power. So basically, it's the same thing as saying that this log base b of b is just going to disappear from this expression. It's just going to leave me with the power. Right? That's what we see here. Log base 10 up to the 6th power, it is equal to 6. So I'm just going to put right here, the solution for this log is going to be a 6. Now, these are the special properties, and there is one more that you can have for your record that we will not be using in this course at this point. It is one of the inverse properties, which is this one. We basically went over the first 3. Now, the next and last thing that we're going to cover here before we get into the graphs is the natural logarithm. Now, a natural logarithm, it is a special log abbreviated as ln, and that log is basically a logarithm with base e. So if I have a function, let's say f of x equals log base e of x, then we can rewrite it into this format, f of x equals natural log of x. By definition, you see that on this log there is no base underneath. That by definition and by default, it is always a base of e. We don't have to express we don't have to write the e on the base whenever we have a natural log, We just have to understand that there is an e as a base all the time, anytime we use a natural log. Okay, so those same properties that we went over, they also apply to natural log. For example, I'm just going to talk about the first three in general. The first three properties tells me that if I have ln of 1 equals to 0, what does it mean by ln of 1 equals to 0? Now, remember that the base of the ln is e. So this means that e raised to what power equals to 1. So not only for e, but whenever we have any base, that's what I specified in this definition. Anytime I have any base raised to what power is always going to equal to 1, power of 0, and it works for any base. That's what you see right here, the solution. Okay, it doesn't matter what the base is. If the result is 1, the power that makes a number become a 1 is always a power of 0. Now, second definition you see right here, it tells me ln of e equals 1. Now, what does it mean by ln of e? Remember that anytime we have a natural log, by definition, we have a base of e down here. So what does this mean? This means that e, I'm just going to put it down here, e raised to what power equals to e. And the power for that, it would be to the first power. For a number to equal to itself, the power must always be 1. So just keep in mind, anytime I have ln of e, that is automatically equals to 1. And then the same thing for the last definition here. This one tells me that ln of e raised to the power of x is going to equal to x. And now the reason is, once again, because this means that you have a base of e down here. This means that e raised to what power equals to e to the x power? Well, it has to be x power. That's what we see right there. And those are the same three special properties that we talked about, general properties that we talked about on the previous questions. Now let's answer one more question here using e, using the natural log. So we have evaluate. We have ln of 1 over e to the 9th power. Now, let's remember one thing. What does the 1 over e to the 9th power means? E raised to the power of negative 9. Remember, the reciprocal makes it become a negative exponent. That's the negative reciprocal rule. And then what do we know about ln of e raised to the negative 1 power? This is a special property. ln of e raised to the x power, it's going to be x. So that means ln of e raised to the negative 9 power is just going to be negative 9. Anytime we have ln of e, the ln of e basically simplifies to 1 or disappears from the equation. Okay. Now we're going to get to the graphs. Okay. Now, these are some of the properties that you need to keep in mind from logs based on the characteristics that I show you from the exponential functions on section 4.1. Now, we talked about the exponentials, and we said that the domain of the exponential functions was from negative infinity to positive infinity, and the range was from 0 to infinity. Now, the logarithmic function is the inverse. So the inverse properties, remember what happens, the domain of the function becomes the range of the inverse and vice versa. So you see that now, originally the domain was from negative infinity to positive infinity on the exponential functions, which means that the range of the logarithmic function, which is its inverse, it is negative to positive infinity. Now, we also talked about on the exponential functions that the range was from 0 to infinity. That means that the domain of the inverse, which is the logarithmic function, is from 0 to infinity. Now, if you remember from the previous section, I also mentioned that these graphs, the graphs of the exponential functions of the form b to the x power, pass through the point 0, 1. The logarithmic function, since it is the inverse, they pass through the point 1, 0. That's the inverse point. And we said that on the exponential functions, they have a horizontal asymptote at y equals 0. Then the logarithmic function have a vertical asymptote at x equals 0. X equals 0 is the same thing as the y-axis. And last but not least, talking about the bases. We said that if the base is greater than 1, the function is an increasing function. The graph is an increasing function. If the base is between 0 and 1, then the graph is a decreasing function. That is still the same. Now, the first thing I'm going to show you is how we can basically graph it using the inverse. Okay, so we're going to go through this problem right here. We're going to graph the function f of x equals 5 raised to the power of x, and g of x equals log base 5 of x in the same rectangular coordinate system. So, let's start with f of x. Just remember one thing. This function 5 to the x power and log base 5 of x, they are inverses of each other. Okay? That log base 5 of x is the inverse of 5 to the x. So, what we're going to do is we're going to create a table for my function f of x. And then how do we get the inverse? By flipping the points. Right? That's how we're going to do. So, we're going to use the same values as usual, which is -2, -1, 0, +1, and +2. So 5 raised to the -2 power means 1 over 5 to the second power, which is 1/25. Now, 5 to the -1 power means 1 over 5 to the first power, which is 1/5. 5 to the 0 power is equal to 1. 5 to the first power is equal to 5, and then the next one is 5 to the second is going to be 25. So, for the function f of x, we're going to get the following points. -2, comma. Now, 1/25, if you remember, we talked about this, is like about 0.04. Like approximately. So, it is an estimate. Now, 1 over 5, it is exactly 0.2. So, this is going to be -1, comma, 0.2. The next one, 0, comma, 1. The next one, 1, comma, 5. And the next one is 2, comma, 25. So, let's graph f of x. -2, comma, 0.04. It is located almost touching the x-axis. Then -1, comma, 0.2. It is somewhere in this region, in this area. 0, 1. It is here. Then 1, 5. And the last one is 225, which is way up here. So this is going to be the exponential function 5 raised to the x power. And what happens as the graph of the x value decreases? We talked about it in the previous section. The graph keeps approaching, but it never gets to the value of 0. Y equals 0. So we said it has a horizontal asymptote at y equals 0, right? This is a function f of x. Now, do remember what we mentioned, that the logarithmic function is going to be the inverse function. So if I want to get the inverse function, all I got to do is interchange the values of x and y. So you're going to see this one is going to be 0.04, comma, -2. This one is going to be 0.2, comma, -1. This one is going to be 1, comma, 0. This one is 5, comma, 1. And this one is 25, comma, 2. Now, one little observation that I want you to do on the logarithmic function is this. What do you notice on the y values? Now the y values will be my -2, -1, 0, 1, and 2 that we usually pick. That's what we're using those for the y's whenever we're graphing a logarithmic function. Okay, that's what we're gonna do on the next couple of problems. I want you to keep that in mind. So this is gonna give us 0.04, comma, -2. So it's basically almost touching the y-axis right here at -2. Then 0.2, comma, -1, it is somewhere in this area. Then 1, comma, 0, it is right here. Then 5, comma, 1, and then the last one is 25, comma, 2. That one is very, all the way to this side, so we don't see it, right? So this is the way the logarithmic function looks like. And it keeps on going. This is my g of x. And what do we know? Now what do we see? As the value of x, as we decrease the value of y, what's happening to the value of x right here? Now the value of x is the one that is decreasing to 0. So it doesn't matter how much we decrease the value of y. So it's going to keep going down. but the value of x is going to keep getting closer to what we call the y-axis. It's going to keep getting closer and closer and closer to the y-axis, but it will never get to the y-axis. This is going to be my inverse function. Remember that the function, any function and its inverse, they must be reflected over the line y equals to x. This is the line of symmetry of the functions. This is basically how the logarithmic function is going to look like. And what you see right here, like I told you in the definition, these functions, they have a vertical asymptote right here at x equals to 0. Okay? Now, based on what I already told you, that they have a vertical asymptote at x equals to 0, and that the values of y will be my -2, -1, 0, 1, and 2, we're going to use those ideas now to go ahead and graph this function. So this problem tells me, begin by graphing f of x equals log base 5 of x, then use transformations of this graph to graph the given function g of x. What is the vertical asymptote? And use the graphs to determine the given function's domain and range. The first thing that I would like for you to do, so that you can basically understand the concept of what we're about to do, is, okay, let's change the f of x to a y right here. So that's y equals to log base 5 of x. What I want you to do is I want you to rewrite this equation in exponential form. What does it mean by exponential form? Remember that the 5 represents my base and the y represents my power, and the x represents the result. So this means that 5 raised to the y power must be equal to x. We're going to use this equation as a basis when graphing this function. Okay? And just like I told you, the y values will be my -2, -1, 0, 1, and 2. That's exactly what we have to do here. So for the f of x, we're going to put -2, -1, 0, 1, and +2. Why on the y values? Just like I showed you in the previous question, because if I want to find the value of x right here, I need to do 5 raised to whatever y power we pick. So now the y values are the ones that we selected. So it will be 5 raised to the -2, which is my y, 5 raised to the -1, 5 raised to the 0, and each one of them is going to give me the value of x, which is what we're looking for in this one. So I'm going to start by doing this. 5 raised to the -2 power, and I'm just going to find the solution, which is 0.04. We talked about it on the previous graph. 5 raised to the -1 power, that one is, we said, is 1 over 5, which is 0.2. 5 raised to the 0 power, that's going to be a 1. 5 raised to the first power, that's going to be a 5. And 5 raised to the second power, that's 25. So it's basically kind of the same thing as what we graphed on the previous graph, or the previous example. So my function f of x has the points 0.04 comma -2, then 0.2 comma -1, then 1 comma 0, then 5 comma 1, and last 25 comma 2. So that's my f of x up here, which is what we're graphing right now. So let's go ahead and sketch the graph of f of x. So we see that we're going to start with the point 0.04 -2, which is almost touching the y-axis down here. The next one is 0.2 -1, so it's somewhere in this area. Then 1 0, then 5 1, and the last one is 25 2, which we don't see it. So the graph of this logarithmic function is going to look like this. And what happens as the y value decreases? We said that the x value keeps approaching, but it never gets to 0. So it just keeps getting close to the y-axis, but it never gets to the y-axis. Okay, that's what we see on the x value. It is approaching 0. So that means what we talked about before. Now on this problem, now we need to graph the asymptote. That's one of the things that we're asked to do. So we're going to graph the asymptote with a dashed line right here. So at x equals to 0, there is a vertical asymptote right here. So before we get into the g of x, so what I want you to do is I want you to write all the things that we need to find from the functions. So, for the function f of x, we need to give the domain, the range, and the asymptote. What is the domain of this function? Well, it starts from any number greater than 0 because it doesn't get to 0. So we're going to say parentheses 0, and it goes all the way to the right, so it keeps on going to the right to infinity. Now, what about the range? This graph keeps going all the way down, and likewise, this graph keeps going all the way up. What does it mean? That all of the values of y, the negatives and the positives, will be on this graph. So that means that the range is going to be anywhere for any number from negative infinity to positive infinity. Last but not least, we need to find what the asymptote of this function is going to be. Now the asymptote is going to be the line x equals to 0 because it is my vertical line right here on the y-axis. X equals to 0. So those are three of the things that we need to answer from f of x. Now we need to do the exact same thing, but now it's going to be for g of x. Now I want you to take a look at f of x and compare it to g of x. So f of x is equal to log base 5 of x. Now if we make a comparison from this to g of x has the function log base 5 of x plus 8. What is that plus 8 going to have as an effect on the graph? We talked about it before. It's going to shift the graph 8 units to the left, meaning that all of the x values are going to be subtracted 8 units. That's what's going to happen to this. All of the x values are going to be subtracted 8. So then we're going to get the new points. And we're going to get the point 0.04 minus 8 is negative 7.96, comma, negative 2. Now, 0.2 minus 8 is negative 7.8, comma, negative 1. 1 minus 8 is negative 7, comma, 0. 5 minus 8 is negative 3, comma, 1. And 25 minus 8 is going to be 17, comma, 2. Let's graph those points now for this function g of x. Now, negative 7.96 and negative 2, negative 7.96 is almost at negative 8. Almost, but not quite. Negative 7.8 and negative 1, it is somewhere on this area right here. Now, negative 7, 0. Then the next one is negative 3, comma 1. And the last one is 17, comma 2. That one we don't see it anymore. So this is what the graph of this function is going to look like. This is g of x. And I forgot to label f of x right here. Okay. So what happens? What is happening now to the value of x? As the value of y decreases, the value of x, it is decreasing to what number now? Negative 7.8, negative 7.96. So it is decreasing to negative 8. And the reason is because we shifted the graph to the left 8 units, meaning that my vertical asymptote, x equals 0, is also going to move 1, 2, 3, 4, 5, 6, 7, 8 units to the left. So this is where my new asymptote is going to be located. So now we're going to graph a vertical asymptote at x equals to negative 8 right here. So what does it mean? That the graph right here, as the value of y decreases, the value of x is going to keep getting closer and closer and closer to negative 8, but is never going to get to negative 8. So let's go ahead and give the domain, the range, and the asymptote of this function for g of x. What is the domain? We see that it doesn't start from negative 8, so it starts from anything after negative 8. So it would be starting from negative 8 with the parentheses, meaning not including negative 8, all the way to the right to positive infinity. Now, the range. You see that this function is still going all the way down to negative infinity, and it is still going all the way up to positive infinity. So my range is negative infinity to positive infinity. And last but not least, the new asymptote for this function is going to be the line x equals negative 8. And these are the attributes for these functions f of x and g of x. Now, we're going to work on the next graph. this one. So we're kind of going to do the same thing here. Begin by graphing f of x equals ln of x, then use transformations of this graph to obtain the given function h of x equals ln of negative x. So we're going to start with f of x again, right here. What I ask you to do to make it simpler is we're going to change the f of x to y, and then we're going to rewrite this equation in exponential form. So this one in exponential form, you see what is the base of these logs. Since we have a natural log, we talked about it before in this section. Anytime we have a natural log, by definition, the base is always going to be e. So that means that that's the base, and the power is always a y on the other side. So it's e to the y equals to this answer of x. That's what my equation is. So we're going to create the table again for this. So I'm going to put that y, instead of y, I'm going to put f of x. So we know that y represents my first function, f of x. Okay. Remember that now the y, again on the logarithm, is going to be my -2, -1, 0, 1, and +2. So if I substitute those values into the y to find my, x values, because x is equal to e to the y power. So to find every x, we're going to do e to the y, which in this case is -2, and use the calculator to find this value. E to the -2, we talked about it before in the previous section. It is equal to 0.1 approximately, so it is estimated. Right? Then e to the -1 power, it is estimated to be I believe it was 0.4. Then e to the 0 power, anything to the 0 power is always equals to 1. E to the first power is estimated to be 2.7, and e to the second power is estimated to be 7.4. Okay, so these are the points for my function f of x. So for f of x, we get 0.1, -2, 0.4, -1, then 1, 0, then 2.7, 1, and 7.4, 2. Okay, so let's go ahead and graph the function f of x. This natural log of x is going to look like as follows. 0.1, -2. So you see that even then, the graph is going to be very similar to the one we just sketched previously with the base of 5. 0.4, -1. 1, 0. 2.7, 1, somewhere over here, and 7.4, 2. 7.4, it's going to be somewhere over here, +2. So this is more precisely of what this graph is going to look like. And it keeps on going up. So I just didn't touch that point, but it's okay. Very close. So this is my function f of x. Now, what happens again? What do we notice that it's going to happen as the value of y decreases? As we decrease the value of y, the value of x, it is getting close to 0. It is approaching the number 0. That's what happens to the value of x. So we're going to go here. That means that as we decrease the value of y, the value of x is going to keep getting closer and closer and closer to 0, which is my y-axis. Okay? So that means, once again, that this graph has a vertical asymptote at the line x equals to 0. This is where my asymptote is going to be located, at x equals to 0. So as we go, I'm going to go ahead and label those things from f of x. So the domain of f of x is going to be from 0 to +infinity. The range of f of x, you see that it goes all the way down and then it goes all the way back up. So that means that it includes all of the values of y from negative to +infinity. And the asymptote of this function, it gets close to, but it never touches the line x equals to 0, which is my y-axis. So that is from the function f of x. Now we have to do the exact same thing, but now for g of x. Now remember that f of x is equal to the ln of x, right? That's the original function. Now we're going to sketch the graph of g of x equals ln of negative x. What does that negative in the x has as an effect? It is going to reflect the graph over the y-axis. That's what the negative in front of the x does. Okay, so if it reflects it over the y-axis, what does it mean? That all of the x's, negative x means that all of the x's on these points are going to be multiplied times a negative 1. That the negative means multiply them times a negative 1. And if I multiply them times a negative 1, all is basically going to happen is that these values are going to change the signs, the x values. Okay, so let's go ahead and write the new points for this. So we are going to get, if we change the signs of the x values, we are going to get negative 0.1 comma negative 2. This one becomes negative 0.4 comma negative 1. This one is negative 1 comma 0. This one is negative 2.7 comma 1. And this last one is negative 7.4 comma 2. Those will be the points for g of x. So let's go ahead and sketch it. Negative 0.1, negative 2. It is almost on the y-axis right here. Negative 0.4 comma negative 1. It is somewhere over here. Negative 1, 0. It is here. Negative 2.7 and 1. It is somewhere over here. And negative 7.4 and positive 2. It is somewhere over here. So this is going to be what the graph of g of x is going to look like. And as the graph, the value of y decreases, the same thing is going to happen. You see that the value of x, it is getting closer and closer and closer to 0. The value of x is still getting closer and closer to 0, but from the negative side. It is approaching 0. So this is going to be the graph of g of x. So then on this graph, we also have the same vertical asymptote because it is getting closer to 0 as well. So the vertical asymptote is still the same. So let's go ahead and find the attributes for this function. The domain is a little bit different because now you see that it goes all the way to the negative side. So it keeps on going all the way to negative infinity to the left side. And then it's going to stop once it reaches 0. So, but it doesn't include 0. Now the range of this function is still going to be, it's going to keep going all the way down to negative infinity, and the graph is going all the way up to positive infinity. So it's going to include all the negatives and positive values of y in the graph. And the asymptote of this function, it is still the line x equals to 0. That has not changed. Right? So that is basically how we graph a logarithmic function. Now something that you notice is that the domain of the logarithmic function doesn't include all the values. It just includes the values of x. Basically, I'm just going to tell you the actual idea. So if we go to this question that we talked about before, you see that this log includes all of the values of x from negative a to positive infinity. Basically, it includes any value of x that makes this expression inside of this parentheses, which is my domain, anything that makes that expression inside a positive number. Okay, so that's basically what the domain of the logarithmic function is going to consist of. Anything that makes it positive inside of here. So then, without graphing, how do we find the domain of a logarithmic function? This is basically how we're going to do it. By just looking at the equation, we should be able to find the domain without sketching the graph. So, the domain of the logarithmic function of the form f of x equals log base v of x is the set of all positive real numbers. So basically, anything that makes this expression right here a positive real number. Okay? So, and what does it mean by a positive real number? Anything that makes it greater than 0. Once again, anything that makes it greater than 0. So let's go ahead and find a couple of domains here. We're going to start with this one here. So find the domain of the logarithmic function f of x equals log base 10, because it doesn't have a base, of 5 minus x. So The domain of any logarithmic function consists of any number, all the numbers that make this expression inside a positive number. What I mean by a positive number, I mean what makes it greater than 0. So this is the equation that we have to set up to be able to find the domain algebraically without having to sketch the graph of the function. So that has to be greater than 0. So if I want to solve for x, I can subtract the 5 from both sides. That gives me negative x is greater than negative 5. And then to leave the x by itself, I have to divide both sides by negative 1. But keep in mind that anytime we divide an inequality by a negative number on both sides or multiply it by a negative, the inequality symbol changes to the other direction. So this is going to be x is less than positive 5. So that's what the domain of this function is going to be. If we were to graph it, then we're going to see that the domain is anything from negative infinity all the way to 5. And 5 is going to be my vertical asymptote of that graph. That's where the graph is going to stop. If it was to be sketched, which in this case we don't actually need to. So we're going to write the domain in two different ways. First of all, I'm going to write it in set notation. The domain in set notation would be the set of all x such that x is less than 5. So we already have it in set notation here. Or if we want to write it in interval notation, we would say if x is any number less than 5, that means that x is any number from negative infinity all the way to 5, not including 5. And those are the two different ways of expressing the domain right here. Now, we're going to be finding the domain of the following problem. Find the domain of the logarithmic function f of x equals natural log of x squared plus 4x minus 5. So, without sketching the graph, in order for me to find the domain, all I need to do is find all of the values of x that make this expression inside of the parentheses right here greater than 0. A positive number, again, it means greater than 0. So, what I need to do right here is solve for x, but if you notice, this is a polynomial inequality. So in order for me to solve a polynomial inequality, we need to first find the zeros of it, and then we need to use the number line to find the values of x on which intervals are the values of x that make that inequality true. So it's basically going back to section 3.6. So that's how we solve a polynomial inequality. So first thing we're going to do here is we're going to change that inequality symbol to an equal sign. And in order for me to solve for this, we need to factor. So to factor the trinomial, first of all, we look for the greatest common factor, which in this case, the greatest common factor is 1, right, on these three values. Then we're going to multiply a times c. A is 1 and c is 5. So 1 times 5 is 5. So we need to find out two numbers that when multiplied, they give me 5. And when subtracted, they give me a 4. So that would be 5 and 1. So we put the factors, 5 and 1, and then we have x and x, and it has to be a positive 5 and a negative 1. In this case, we don't need to divide because the value of a is 1. If we divide them by 1 right here, it's going to stay the same. So then we're going to set them equal to 0 and solve for x. So we say x plus 5 is equal to 0, so that means that x is equal to negative 5. This one is x minus 1 is equal to 0, so that means that x is equal to positive 1. In reality, in terms of the logarithmic function, those values that we just found, those are my vertical asymptotes of the graph. So this function has two vertical asymptotes because it is a quadratic, so we expected that. So now, we need to find the solutions for that original inequality up here. We need to first of all plot those numbers in the number line, and then we're going to divide it into intervals. Okay, so that's what we need to do next. So my two numbers will be negative 5 and positive 1. So I'm going to plot them right here on the number line, negative 5, and divide it into interval right here. This is one interval on the left side. And then a positive 5 right here, positive 1, and right here there's going to be two more intervals. This one in the middle and this one on the right side. So What we need to do to find out which values make it true and false, we need to use test points. And the test points have to be a number on this interval. So one of the intervals is from -infinity to -5. So we can use -6 on this side as a test point, or -7, or -8, or -9. You know how to do this part. Then any test point that we can use between -5 and 1, if we can use 0, or -1, or -2, or -3, or -4. Now anything on this side we can use, for example, a 2 as a test point. So we're going to substitute them into the original inequality, which is this one up here. Okay, so x, which is -6 squared plus 4 times x, which is -6 minus 5, has to be greater than 0. -6 squared is a 36. 4 times -6 is -24 minus 5. 36 minus 24 is 12 minus 5. It's going to be 7. Is that greater than 0? That is going to be a true statement. What does that mean? That if that makes it true, that means that any number from -infinity all the way to -5 is going to make that original inequality true. Now for the next one, we're going to evaluate 0. So it would be 0 to the second power plus 4 times 0 minus 5 must be greater than 0. So that gives me a 0 plus 0 minus 5, and that is going to be a -5. That is greater than 0. That is going to be false. So what does it mean? That all of the numbers between -5 and 1 are not solutions of this inequality, meaning that these values will not be in the domain of this function. Now we're going to try the positive 2. So this is going to be 2 to the second power plus 4 times 2 minus 5 has to be greater than 0. So it's going to be a 4 plus 8 minus 5. That's 4 plus 8, which is 12 minus 5, is going to be 7. Is that greater than 0? That is also a true statement. What does it mean? That any number between 1 and positive infinity is also going to be a solution. In other words, they will be in the domain also. So for the domain of this function, we're going to say that the domain is any number from -infinity to -5, which is this section right here, or any number from 1 all the way to positive infinity. Those are the values that will be in the domain of this function. Now, what we can do also is that we can check it graphically, so you can see that the graph will contain those values of x in the domain. So I'm going to clear this out right here. So we're going to put ln, which is natural log, is down here, of x squared plus 5x, plus 4x, plus 4x. Then it's minus 5. And then we close the parentheses. If you graph it, this is going to tell you the truth. The domain, you see that exactly where it stops, which is right here at -5, you don't see it, but there's a vertical asymptote, meaning that the graph just keeps on going down at this location. So the domain is anything from -infinity, and it stops at -5, and then it resumes back from +1 and goes to positive infinity. That's what we see graphically that the domain shows us. And the last question, we're going to do the same thing here. Find the domain of the logarithmic function without graphing, just by doing the algebraic method that I show you. So to find the domain of this function, what we have to do is we have to find the values of x that make this fraction right here greater than 0. This is the inequality that we're trying to solve. Okay, so the first thing that we're going to do is we're going to find the 0 of the function right here. So to find the 0 of the function, we have to equal it to 0, and then we need to get rid of the fraction by multiplying the denominator x minus 1 on both sides. Remember, this is how we solve a rational inequality from section 3.6. So this gives us x plus 2 equals, if I multiply these two times 0, I'm going to get a 0. Then I need to subtract 2 from both sides, and that gives me x is equal to -2. I'm going to do the same thing for we also need to find the zeros of the denominator. Remember, that's another part. Zero of denominator. So we need to find whatever makes that denominator x minus 1 equals 0, and that would be x equals to positive 1. So these are the two values that we're going to plot on the number line. So let's go to the number line, and we're going to use the test points to find the solutions for that inequality, for that rational inequality. So we had -2, and we're going to put a division here for the interval, and then we have a positive 1, and we're going to put another division for that interval right here. So we need to pick the test points again. So what could be the test points that we can use in this problem? So on the left side, we could use -3 or -4 or -5, anything as long as it's less than -2. In between -2 and 1, we can use 0 or -1 or any decimal if you wish. After 1, we can use 2 or 3 or 4 or 5 or 6 or 7 or anything as long as it's greater than 1. So I'm going to use 2. We're going to replace them into the original inequality, the one that we're trying to solve, which is this one. So x, which is -3 plus 2, over x, which is -3 minus 1, must be greater than 0. So -3 plus 2 is -1, over -3 minus 1 is -4, is greater than 0. -1 divided by -4 is 0.25. Is that greater than 0? That is going to be true. What does it mean? That anything from -infinity to -2 is going to be a solution for the domain because it's going to make it true. The next one, x, which is 0, plus 2, divided by x, which is 0, minus 1, is greater than 0. So we get 2 divided by -1 is greater than 0, which is -2 is greater than 0. That is going to be a false statement. What does it mean? That any number between -2 and positive 1 is not a solution because it's going to be false. Last but not least, x, which is 2, plus 2, over x, which is 2 minus 1, must be greater than 0. That's going to be 4 over 1 greater than 0, which is 4 is greater than 0. And that is true. Since that one makes it true, that means that anything from 1 to positive infinity is also in the domain because it's going to make that original inequality true. So then we can write the domain of this function. The domain is any number from -infinity to -2 or any number from 1 to positive infinity. And this concludes section 4.2, which is logarithmic functions.